Beginning equilibrium notes for dual credit. So any bond or intermolecular attraction that can be formed can be broken. That's reversibility. These two processes reign in dynamic competition equilibrium, sensitive to initial conditions and external perturbations, Le Chatier. And we'll talk about that later. So just to remind you about reversible reactions, you've had several that you are familiar with, including evaporating condensing water, dissolving precipitating a salt, and there's some biological ones I list out. Reversible reactions are not just limited to chemical reactions, they can be physical processes as well. Reversible processes must occur in a closed system, and both the forward and reverse reactions occur at the same rate. At this point in time, that system is considered to be dynamic equilibrium. So, again, forward and reverse reactions occur at the same rate. The concentration of reactants and products no longer change. So one of the things we've looked at in our activity that we looked at the concentrations and how the concentrations start. They're the same. They're no longer changing. They're no longer high or low. They're just the same rate. A few others that we can also observe: temperature, pressure, and so forth. Concentration of reactants and products are not necessarily equal, and usually they're not. They're just simply no longer changing. That's a dynamic equilibrium. The forward and reverse reaction have not stopped, and they must occur in a closed system. So an equilibrium constant. It is the product reactant ratio. That's called our equilibrium constant. We write the expression based on the law of mass action. Basically means I've got a balance equation. And so I give you the two ways that we'll write it, the Kc and the Kp. Notice they're very similar. One has to use square brackets, one uses a parentheses and a P for pressure. There are no units, and for heterogeneous equilibria, we do not include the solids or pure liquids like water. The reason is that the concentrations are constant. So there's only one value for K at any given temperature. So a lot of information on this slide, but the meaning of the value of K is even though at equilibrium the rates of the forward and reverse reactions are equal, it does not mean that both possess equally favored. That's a thermodynamic sense. So at a given temperature, the forward or reverse reaction is usually more favored than the other. So one's going to be favored than the other. Both the value of the K, and I can have K is greater than 1, equal to 1, or less than 1. And the magnitude of K, which is greater than or less than 1, provide us with a meaningful information about the relative rates of the opposing process. So if the forward process is more favored, there are more products than reactants at equilibrium, and K is greater than 1. For very large K values, we indicate that the products are heavily favored. The reaction is said to lie to the right, and these processes are said to essentially go to completion, as in the case of a strong acid deprotonating. Sorry, it's a typo. If a reverse process is favored, then K is less than 1, favoring the reactants. A very small K value lie to the left, indicating that the reactants are heavily favored. An example of this would be the small, the dissolution of insoluble salt. The meaning of the value of Q, which is another one we're going to look at, it is the relative ratio of products to reactants is expressed in the quotient Q. Q is calculated the same way as K. The only difference is being that the system is not necessarily at equilibrium. So K has to be calculated at equilibrium, Q does not. Oops. So comparing K and Q, the reason I want to know those two is that knowing the value of K and Q allows us to predict the direction a system must progress to reach equilibrium. And again, it's going to be a closed system. So if K is less than Q, the system is not yet equilibrium. Q is too large. There's too many products compared to reactants. Q must decrease to reach K. Therefore, the system will proceed to the left to reach equilibrium. Products will decrease. Reactants will increase. If K is greater than Q, the system is not yet at equilibrium. Q is too small. There's not enough products compared to reactants. Q must increase to reach K. Products must increase. Reactants must decrease. Therefore, the forward reaction is favored. If Q equals K, the system's at equilibrium. So memory trip is to write K and then Q alphabetically. Then you put your values underneath you figure out which one's the greater one, you put your symbol there, you add a tail, and it tells you that which way it's going to proceed. So in this case, the reaction proceeds to the right. It's a great memory tool to remember how to do this. Okay, so just again showing you, this is how I write KC, this is how I write KP, the similarities between the two of them. Again, the superscripts are based off the coefficients out front. These are some additional practice problems for you to look through. So I like the difference of these that I have put on there. So on the very first one, I have a KC and a KP because I am working with gases. On the next one, on the iron 3 chloride, I have a KC, but I have no gases, so I have no KP possible. With the calcium carbonate, I circled the fact that you have solids involved, so there's only one thing that's involved in the KC, which is the CO2. And there's it can also be a KP because I do have pressure. And then I have the copper and silver reaction. And since I have aqueous involved, since I have solids involved, they're not part of it, but the aqueous is, and that's what I have there. Also notice that I do put the charge for the ions in that. So additional practice, this is what we're building towards. It's called ICE or the RICE table. R is referring to the reaction. So I is referring to initial, C is referring to change, and E is referring to what happens overall. So, sorry. All right. So basically, I took from the prompt and I put my initial stuff in there. Then I put in what the change is going to be, and then I put in what the ending amount's going to be. Once I have that, and I've already written my KC expression, I'm just going to sub my numbers in, and I get a number. Here's another practice one as well. This one just happens to be pressure. Again, I'm setting up the same thing, ICE, and I'm putting in my KP, and I just put my numbers in and I solve for it. So I can convert between KC and KP. So when all the species, reactants, and products are gaseous, either KC or K in terms of concentration or KP in terms of pressure can be used. There's a way to convert between KP and KC. The formula is no longer provided on the AP formula sheet, so you're going to have to be able to memorize that and know how to do it. The main thing is also to make sure that on the R, you are using the right R depending on the pressure unit. You've seen this before in gas laws. So here I just have you an example of how I do this. So you're going to calculate the difference in the number of moles of gases. In this case, the difference is 2. I have 2 moles of products, 0 moles of reactants. I'm going to substitute the values in the equation, and I'm going to calculate my Kp. So as you can see, I put in the 6.96 times 10 to the negative 5th. I have the 0.0821 because it's based on my pressure. Then I have the 380.33, and I'm going to raise that to the square, and I get 0.052. Here's just another example. I can produce a negative. So in this case, I have 2 moles of products minus 3 moles of reactant. I get a negative 1. So I take what I have there and I raise it to a negative 1. I get a Kc of 73.5. Okay, match your R to the pressure units. This is our activity that we did. Just going over what we got for the answers. We also looked at the graphs on that. All right, position versus constant. This is a product reactant ratio, only 1 K value for any given temperature. So again, I just going back through what the K means and what it means as far as which way it's going to swing. So repeating information I'm done. Calculating K from equilibrium positions. Same thing I'm already mentioning, just going back over it. Looking at this one, what do you notice about the values for the two experiments? They're the same. Which numbers represent the equilibrium positions, the actual concentrations at equilibrium. We talked about our graphs here. We looked at lots of graphs when we did our stuff. So here's 2 different ones. I have one where they cross, and so the K is greater than 1. So at equilibrium, I'm moving towards the reactant. The reaction is favored. The reaction lies to the right. And on the other one, K is less than 1. So my reverse reaction is favored, so the reaction lies to the left. Oops. And then I just had you do particular diagrams because we all got to practice that. If I start with 10 dots, I got to end with 10 dots. The main thing I want you to focus on this. And so you just see the progression as it goes through time. And eventually, I end up with 3 purples and 7 blue, and it doesn't matter how much time progresses, I'm still going to have 3 purples and 7 blue unless I do something to cause a system change. Manipulating K for the reverse reaction. The main thing is if my forward reaction is, say, 250, then my reverse reaction is going to be the inverse of that, or 1 over 250. The reverse is going to be the inverse. Okay? For reaction to multiply by n, I'm just going to raise it to the n. For 2 reactions which are added, you can see it's going to be Ka times K2. Reaction quotient Q. Q is a reaction quotient. Calculated the same way as K, but the system's not necessarily equilibrium. That's the main thing, okay? And I've already gone over that y'all can read through that again. All right, I've already talked about the Rice tables. We make an equilibrium expression. We set up our Rice tables. That's right, so our E is equilibrium. And I substitute, solve, and I check it to make sure it makes sense. Here's some example problems. So you can look over those and see what I'm doing there. I'm just simply just subbing in and getting a number. And there's another problem example right there. And then we talked about in class about disturbing a system. I can change the concentration, I can change the pressure, I can change temperature. Anytime I make those changes, that's a Le Chatelier principle idea, and we'll be looking at that. So just because I'm in equilibrium doesn't mean I stay at equilibrium, because if I stress it, it changes it. And that's it.